Okay, we're in section 24 of the notes, basically a continuation of 23. Certainly we'll look through this. I see an image initially with the function written down over here. My suspicion is they're going to ask questions about this function and that image. What kind of question going to ask? Certainly pre-calculus questions, but also calculus questions. For example, maximum, minimum, points of inflections, so forth and so on. We'll certainly answer each of these questions separately, and we'll go through that later, right? As we go through that first example, then we're going to summarize again what we said in the past. Again, what's critical here is you have certain things down. For example, the first derivative test and the second derivative test. First derivative indicating where the function is increasing, decreasing. Excuse me. Second derivative indicating a concavity, whether it's concave up or concave down. All right. There's some other information over here. I'll read through that for you. Certainly, we would also recommend you reread that as you start to study the material to become more familiar with what we're saying over here. But again, so those two big tests that we talked about, the first and second derivative test, if you could focus on that, you're going to do well with the questions that are going to be presented to you. Do you need to remember stuff from the past? Of course you do. Like closed interval method, Rawls theorem, mean value theorem, that was given to you in the past, right? Then we'll go to examples, and hopefully as we go to examples, things will become more clear to you about what's expected. So I'm going to go back to the beginning of 24 and go to my whiteboard. And as I do that, again, I would recommend you also try to either take notes or try to follow along by taking your own notes, doing your own work. So give me a second. Okay, so we're not really in pre-calculus at this point, we're in calculus. So what I would claim over here, if I were looking at this problem over here, one thing I notice about it, there's no X and Y axes. So I don't know where this thing is, other than that fact that tell me that this is a graph of the function. Right. What I'd like to do though, is just simply go along and write down things I might write down. Right. So what might I write down? And we'll look at the questions later. Looking at this, let's talk about the things you might have done in Math 119. In Math 119, you might have just simply said, what's the domain of the problem? Well, the domain of this problem over here is all the real numbers. Range was more difficult. We'll do that later. But in 119, range was far more difficult. All right. What else would you have done in Math 119? You might have done for, what's called the Y-Intercept. I'll write this over here. So Y-Intercept. Again, we're trying to target really simple questions over here. I want to claim, though, this is the function over here. This is what we need to focus in on. So what do we get? What's the Y-intercept? Well, you said X to be 0. And what would Y be? Y would be 0. X-intercepts. It's really the same thing. It's 0, 0. So far, so good. Pretty easy. What else would you have done in Math 119? Well, it's a rational function. You would have looked for asymptotes. There are no vertical asymptotes because the bottom is never going towards 0. Now, what do I have, though? I might have a horizontal. So let's look at that. Limit as X goes towards infinity of f of X. We'll just look at that function. Fairly easy to do from 119 level. The bottom's growing much faster. It's going to be 0. Limit X goes to minus infinity. And again, the bottom is growing so much faster. It's still 0. So I'm going to put that information down. And, certainly looking at the picture, well, I guess there's something else I could do from 119. I could look at symmetry. Now, looking at it, I'm going to say it looks like it's odd, just looking at the picture. What does that mean? F of X would equal the opposite of f of minus X. So I'm going to look at it, but I can verify it. So f of X is just X over X squared plus 9 minus, what's f of minus X? Minus X. Whoops, sorry about that. I forgot to put the equal sign there. Let me go backwards. I'll write the 9 a little better too. Well, the opposite f of X can be minus f of minus X, which can be minus X over minus X squared plus 9. What do you get over here? X over X squared plus 9. Well, that's not so difficult. What do you get over here? Well, minus of minus X, just X. And on the bottom, you get X squared plus 9. So it's definitely odd symmetric. What does that mean? Symmetry about a point, that point would be the origin, which is going to be our y and x-intercept. So I'm going to say over here is that point now. And what's that point going to be? 0, 0. What else do I know? There's a horizontal asymptote and it's 0. I'll put that down for you. It's an asymptote over here. And this is y equals 0. That's a horizontal asymptote. I guess I should write that down. Horizontal asymptote. We're just going through the 119 material. Y equals 0. What else would you do on 119? Probably just simple sign analysis. After the 0, you plug it into the problem, take a number like 1, plug it in, it's positive. Below the 0, take a number like -1, plug it in, it would be negative. So I get a feel that this thing does something like this. And here comes a problem in pre-calculus is connected together, right? Now, what do I know? Let me point out what I mean by that. I know over here it's positive, and over here it's negative. And I know the function's odd. So I'm going to say, this is not bad that they gave me this picture over here. And I'm going to kind of trace that in for you now. And again, I'm glad they gave me the picture. All right, I'm glad they gave me the picture. Now, what do I know about this? If you went back to 119, you probably would, you might be asked a question like, use technology to determine the min-maxes in the problem. And I'm kind of looking at it, and I see them over here. That would be what's called a local, because of an open interval, local max. But also just looking at it, I would say global too. How about this one over here? Local, again, because it's an open interval, and that would be a minimum, but it's also global min. Right, global too. So we're going to switch ships or whatever. And I guess we're going to put the calculus down. All right, we'll talk about that. I'll tell you what the calculus is going to give you. Now, this might be tough, but I got to get derivatives. And then we'll look at the question what they asked. Maybe we've already answered the questions. Who knows? So f of x is, let's see, x over x squared plus 9. And so f prime, square the bottom, that wasn't so bad. Bring the bottom to the top, times root of the top, minus the top, times the derivative of the bottom, which is 2x. I got to clean it up. And what do you over there? You would get 9 minus x squared on top. What do you get on the bottom? X squared plus 9 squared. Let me put my critical numbers down. And again, the demand is all real numbers. There's only 2 critical numbers, plus or minus 3. You should be getting better with sign analysis now. Take 0, plug it in. What do you get? Positive. What does that mean? The function's increasing. If I took a number after 3, plug it in like 4, it would be negative. That means the function's decreasing. And if I took a number below minus 3, like minus 4, plugged it in, it would be minus, and that means it's decreasing. Well, looking at it, I'm pretty much convinced this is a min. And I hope when you're looking at this over here, I hope you're convinced it's a max. I think I can write those points down now. Let me put on what I mean by that. This point here, right, I can write this down now. What's going to be 3, f of 3. What's this point over here? Minus 3, f of minus 3. Again, we haven't looked at the question yet. We're just going through what we know at this point. All right, what I'll do now, well, after I do the first derivative, I probably would go for the second derivative. So let's put that down. And the second is going to be about concavity. Oh, that might be tough. I have to square the bottom, right? So it's x squared plus 9 to the 4th power. Bring the bottom to the top, leave it alone. And that's x squared plus 9 squared times root of top, which is minus 2x, minus the top, which is 9 minus x squared, times the derivative of the bottom. And that's going to be 2 x squared plus 9 times 2x. All right, I'm going to get busy factoring it. I know this is painful, but we really want to recommend that you have to practice algebra to get good at calculus. So I'm going to factor out x squared plus 9. And I'm going to factor out a minus 2x. And what would you be left off with? X squared plus 9. That's from the first term. The second term, what would you get? What would you get plus? Well, it's gonna be a tough one. I guess you get 9 minus x squared now. I want to tell you one thing nice about having pictures. If you have pictures, it's going to allow you to know if your derivatives are wrong, at least somewhat so. We'll go through that in a second. X squared plus 9 to the third power. You may what I'm doing over here. I'm looking at these two factors and canceling one of them. And what do you get on top? Minus 2x. And then you get, x squared minus x squared. There's no x squareds. Well, you know what? I forgot a 2. I just noticed that. Sorry about that. So you're going to get, let's see, 1827. Put this over here. Minus x squared. Okay. Whoops. So what's the point of that? And again, I'm not going to say that that's the right derivative. I don't know. I'll check my key later. But I'm just playing around with what I know so far. And where would this thing take on a 0? At 0. When I talk about the critical numbers, the only critical numbers where it takes on a 0, and plus or minus the square root of 27. All right, I'll write that over here for you. You can write this down as 3 root 3 if you prefer. All right, let's take some test values. And again, I hope you're getting better at this. I'll point out what I'm doing though. I'm going to choose 1 here, minus 1. And over here, I'm going to choose 10. Over there, I'm going to choose minus 10. Again, you could choose any number on an interval. Let me try 1 first because it's so easy. And if you try 1 first, it's so easy to try. That's why I'm trying 1 first. What do you get? Negative on top, and the bottom is always positive, so negative. This is the second derivative we're analyzing. What does that mean? Concave down. We'll look at the picture later. I'm going to go after, root 27. I'm going to say 10. And on top, what do you get? Well, you would get a negative times a negative, which is a positive. What does that mean? Concave up. We'll look at the picture later. Let's do minus 1. If you plug it in, you get positive times a positive. That's a positive. What does that mean? Concave up. If I took minus 10, I'd get positive times a negative, which is a negative. That means concave down. Well, I'm going to look at my picture and see if that's true. If I'm getting what they said I should be getting. And let's take a look at 0. To the right of 0, it should be concave down. I definitely see that, by the way. I'm seeing concave down over here. And then it's someplace over here, it goes concave up. And they're saying that's true. And that occurred at this point over here is a point of inflection. And that occurred at 3 root 3 f of 3 root 3. Right, yeah, that can be computed. And then, looking at my analysis is concave up. And then it goes concave down. Well, I'm seeing that. Here's a point of inflection. And what's that point of inflection? Minus 3 root 3 f of minus 3 root 3. We'll clean this up in a second. All right. I think that's about all I really can do at this point. And now I'm going to see if I can answer the questions. What's the first question? What's the domain? Do we answer that? That's one of the first questions we answered. Oh, you know what? I didn't write range down. I'm going to do that now. And that's going to be f of minus 3, comma. How do I know that? That's the lowest point ahead. What's the highest point ahead? F of 3. I'm sorry, I should have answered that. So our x-intercepts, yeah, we did that before. There's an x-intercept. What was it? 0, 0. That's indicated. Any y-intercepts? Yeah, we did that right from the get-go. 0, 0. Let's go to the next page, see if we can answer that. Symmetry. I hope you remember we did that. We've already did that. It's something we've done in the past. Let's see how we did this on the first derivative. They said it's 3 minus x, 3 plus x over x squared plus 9 squared. Let's see if I did that. Wow, seen it right over there. They just factored it. That's all they've done. All right, let's take a look. Points of extrema. Well, it looks like they did some arithmetic, but I didn't do it. Right, but they got to 3 or minus 3. Minus 3 is where the minimum occurred, and 3 was where the maximum. I want to point out, it's really not bad to compute these numbers. So, what's f of x? Well, that was, let me go back and show you. That was x over x squared plus 9, right? So what's f of 3? That would be 3, and that would be 9 plus 9, which is 18, which is 1/6. So I'm pretty comfortable with that. And f of minus 3, very simple. It's minus 3 over 18, which is minus 1/6. And again, I'm comfortable with that. All right. Okay. Intervals where it's increasing. So let's go back. I didn't answer that, but I think we know what it means to increase. Whoops, sorry about that. Here's the interval where it's increasing. It's increasing here. What's that interval? Minus 3 to 3. Go back, make sure it's written down for you. Again, you would write that down. How about where it's decreasing? Well, if you go back over here, I want to point out it's decreasing here. That's minus infinity to minus 3. Again, this is decreasing. And it's also decreasing over here. And where's that going to be from 3 to infinity? It's decreasing here as well. All right, let's go back over here. And again, we're just talking through the notes. So all we're doing. So I see that. Now let's see if we got the second derivative. I don't know, maybe I made a mistake. Let's take a look. I'm going to copy it. Let's go back over here. I'm going to paste it in here. And I want to be critical. I want to see if I did a good job. I noticed that there looks a little different, right? Most I did was factor out a -1. So I'm going to say it's identical. So this and this are the same thing. Let me put a red check. We did good. All right. Now let's see if we go to the next question I have. And I guess the next question is find the points of inflection. And did I do that? Well, I said they occurred at -3√3 and a 3√3. All right. Let me point out what I mean by that. I got to go back. Sorry about that. Remember, I said there was points of inflection here, here, and here. Let's go back to this. Oops, I got to get to that page, right? So remember, I said here, here, and here. There were points of inflection. What I noticed is they computed the numbers, though. Let me put, I just put it down like f of. Let's write this down. What's f of x? Let's see if we can get those numbers. It's x over x squared plus 9. So let's just do f of 0 first. That gives me 0. That was simple. All right, I should have done that, right? By the way, I don't know if I did that in my graph, by the way. Let me go back to my graph. I think I forgot to write that down as a point of inflection. This is all, and I forgot to write that down. But again, my graph tells me that's a point of inflection, and my analysis says point of inflection too. Where the points of inflection, where the concavity changes, and these are definitely on the curve, where the concavity changes. There's 3 points of inflection. All right, let's go back, and I want to compute the numbers now. And what are the numbers going to be? Well, I did f of 0, and I want to do now f of 3√3. What do you get there on top? 3√3. What do you get on bottom? Well, you'd get 36. Again, square 3√3, add 9 to it, you get that. And that would be √3 over 12, right? All right. Am I seeing that? Right over here. Let me do f of minus 3√3. What do you get? Minus 3√3, again, over 36. Again, simple arithmetic for the most part. You get minus √3 over 12. Are we getting that over there? Of course we are. We're doing okay. All right, let's do the concave up. All right, let's go back to my thing, and I'll point out where it's concave up. It's concave up here. If you were to write those intervals down, I generally just put down CU. Whoops, that's not a U, is it? Concave up here. Where's the concave up? From minus 3√3 up to 0. Where else is the concave up? From 3√3 off to infinity. All right. It's concave up right over here and there. Where's the concave down? Let's write this over here from minus infinity up to minus 3 root 3 union. Where's the concave down? Also from 0 up to 3 root 3. All right, let's go back to the key. And we're over here. And I think we wrote those down, if you remember. Concave down. All right. Okay, so we're done with that. Let's do another little example we do just to make sure you understand what we need to do. Pre-calculus and then calculus. The big thing about calculus is just the first and second derivative. Of course, someone's going to say, oh, you're writing all kinds of things down, asking me to read. Well, it's nice if you can. All right, let's summarize. We're going to summarize now. I'm going to tell you these first 4 things are really important. So when the derivative is positive on the interval, f is increasing, and this should be intuitive as well. If f is less than 0 in the interval, f is decreasing. If the second derivative is positive in the interval, f is concave up. If the second derivative is negative on the interval, f is concave down. These are things that we're saying are intuitive. Again, let me read the other stuff to you. It may be more difficult for you. There's no doubt about it. This may be more difficult. All right. So it says, suppose A is a point in the domain of F. F has a local minimum at A if F at A is less than or equal to the values of F for all points near A. What does it mean? Open interval. All right. This is local. It's got to be on an open interval, left and right. Near means that we need points to the left and the right of A. That's fair enough. All right, local maximum. F has a local maximum at A if F of A is greater than or equal to the values of F for points near A. What does that mean? Open interval. All right, that means there's points to the left and right. All right, left and right of A. And that certainly, again, it's really kind of keeps repeating it over and over again. All right, finding local extrema. Again, this might take more effort on your part. For any function f, a point A in the domain of f, where f prime of A equals 0, or f prime of A is undefined, is called a critical point. We've been doing this for some time, by the way. In addition, the point A, f of A on the graph of f is called a critical point. All right, let's keep moving. The first derivative test for local maximum minimum. Suppose A is a critical point of a continuous function f. If f prime, and again, this requires thinking. If f prime changes from negative to positive A, we have a local minimum. Let me point out what reading it you may want to do with a piece of paper and pencil. Draw a line down at A, the derivative, what do they say? Changes from negative to positive at A. Is what you're saying? What does it say? It's a local minimum. Well, you know what? We've been doing this with our pictures. That's all that's saying. And I see that. I see minimum over here. All right, let's do the next one. And what's the next one going to be? This one over here. Again, it's nice if you can think through this. If the derivative changes from positive to negative at A, then f has a local maximum at A. Well, let me put down what they're saying over there. Whoops. They're saying it changes from positive to negative. What I've been doing? I've been doing things like this. What is this indicating? A maximum, as they said it would. All right, second derivative test. I realize this stuff can be overwhelming. Reading is an important skill set to acquire. Let's go for this. Second derivative test for local max and minimum. Suppose A is a critical point. Because that it says over here. And again, we'll visualize what they're saying. If f prime of A equals 0 and f double prime is positive, I want to point out what they're really saying to me over here. I'll draw a picture of it. So what do I got? I know that they're talking about, you know, the first derivative over here. And they say at A it's 0. And I normally put this over here. Then what do they say? They say the second derivative is positive there. Now what does that mean? It would be concave up. So what does this indicate to me? Certainly a minimum. All right, let's do the next one. And what's the next one? And I'll read it. It says if f prime of A equals 0, but the derivative, second derivative is negative, means concave down. Let's draw a picture of that. All right. So I'm going to put this over here. I'm reading. as you read, paper and pencil might be important for you. This is F prime. I know I got a zero, so put a circle on it. Now, what do they say? It's concave down. What is that indicating to me? Maximal point, as they said. All right. So they go on to say, if f of a is equal to 0 and f double prime equals 0, the test fails. It tells us nothing. Carefully look at your pictures. That's what we're going to say about this over here. So, concavity and points of inflection at points at which the graph of f changes concavity. It's got to be on the graph, though. If it's not on the graph, it's not a point of inflection. It's going to be called an inflection point. It must be on the graph of f. Right. So what do we do now? We're at this interface over here, right, where we talked about lecture. We want to, example we've done before. We've talked about some things, reading through it, not to memorize, but to think. Maybe take a piece of paper and pencil, draw pictures of what they're saying, try to make sense out of it. To memorize? No. To understand? Yes. Then what do you have to do? We have to work on examples together. The intent of us doing this, though, is after we go through the lecture and do examples, you should study that material, and then you should say, I want to start trying this on my own. And we give you problems to try on your own. All right. You want to get busy with that at some point. But right now, we got to get to the examples. Thank you for paying attention.